This demonstration is related to edge intelligence, where an ML-assisted resource management training and deployment in a heterogeneous multi-reflecting intelligent surface setting is considered. Developments have been carried out to integrate machine learning algorithms specifically designed for federated learning at the D6G Edge site. Here, the basic setup of the problem is depicted. The decisions are the phase configuration of each RIS, and the configurations are to be adjusted to enhance some objective criterion, such as the sum rate of the edge communication. Solution approaches based on classic optimization are not appealing due to the nature of related optimization problems within the setting, for example, non-convex and combinatorial. Thus, a data-driven approach is considered, which is more amenable to practical implementations. In the case of our proposed data-driven approach, we assume that each local site has the knowledge of the channel measurements and the corresponding optimal configurations from their prior resource management experiences. This experience is in fact the labeled dataset used when training a neural network model that predicts the phase configuration given the channel measurements. We facilitate the possibility of data being private and heterogeneous among different sites. Thus, the proposed approach is more realistic in practice since the equipment can be owned by different operators, and the user distributions and the corresponding channels need not be homogeneous over different sites. A federated learning within an invariant risk minimization formulation is considered because heterogeneity hinders the direct applicability of classic federated learning. Privacy is intrinsically guaranteed since data are kept locally. Initial results of the research with software implementations are documented in the publication mentioned below. Within the scope of Work Package 5, the federated learning algorithms developed and tested locally within the software are to be integrated into the 5 tonic framework as a prototype. The implementations are to be conducted in 4 stages. The first stage is the integration of classic federated setting in local machines in Oulu. The second stage is the integration of classic federated setting in 5 tonic testbed. The third stage is the integration of federated learning games for reconfigurable intelligent surfaces via causal representations in local Oulu machines. The final stage is the integration of federated learning games for reconfigurable intelligent surfaces via causal representations in the 5 tonic testbed. 4 stage developments are completed. Here onward simulation for Stage 2 and Stage 4 will be presented and compared. Please recall that Stage 2 is the classic federated learning setup in the 5 tonic testbed. As shown in the diagram, parameter server and clients are deployed in the 5 tonic testbed. We use WebSockets as the communication protocol for seamless and efficient communication. As you can see, the parameter server and the 2 clients are already running in the 5 tonic testbed, and a third client is running in Oulu site. The end user can send requests to the WebSocket endpoint in the parameter server with a JSON as payload. We use a Python script to get the intended parameters from the end user. The script will capture the parameters and form the JSON payload and send the request to the parameter server. The script to send the request is run from a local device in Oulu. First, we take the task name as a parameter. This is a unique identifier assigned to the current task. Results are stored under this identifier. Next, we need to select the algorithm to run. In this case, we select Classic Federated Learning. After that, a local mini-batch size should be assigned for the model training. Then the number of local training rounds for each communication round should be defined. In the next step, a learning rate for the optimizer should be entered. As the next input, a client fraction should be assigned. The client fraction defines how many clients should be involved in training in each communication round. Since we use all the clients at each round, we use client fraction as 1. After that, a test mini-batch size should be defined to use during the testing. Total number of communication rounds is taken as the next input. Number of communication rounds define how many model aggregation rounds are occurring in the training phase. Then we need to select a suitable optimizer for training from the given options. We are using Atom Optimizer in this case. Next, a loss function must be selected, and in our case, we use cross-entropy loss as the loss function. Finally, the dataset folder name must be entered. This is the folder name where the training datasets are in each client and the test dataset in the server. Once all the inputs are given, the script forms a JSON payload and sends a request to the WebSocket endpoint in the parameter server. The parameter server starts the federated learning process by broadcasting the global model and hyperparameters to the clients. In the next step, clients start the local training process for the specified number of local epochs, and the resulting model weights are communicated back to the parameter server. The parameter server then aggregates the local models to update the global model, and test accuracy is calculated using the local test dataset. Then the updated global model is broadcasted back again to the clients for the next communication round. This process is continued until a stopping criterion is satisfied. Meanwhile, all the intermediate progress is communicated to the end user during the training process. Once the training process is completed, the models are stored in each client and a repository for later use. Also, a file with the task name containing plots for the training metrics is stored in the user device to examine the model performance. This concludes the results for Stage 2. Next, we run the experiment for Stage 4 to compare the results. Recall that Stage 4 is the integration of federated learning games for reconfigurable intelligent surfaces via causal representations in the 5-tonic test bed. Here, the same Python script is run as before to get the necessary values for parameters by the end user. First, we select VFL games as the algorithm. Then we input the task name. For this, we name the task as VFL games. As the next parameter, the training mini-batch size should be given. Here we fill it as 256. The next parameter to input is the learning rate for the representation learner model. Unlike in the classic federated learning setup, we utilize two neural networks, representation learner and the extractor model. Representation learner is a common neural network used by all the clients, and the extractor is unique to each client. The output of the representation learner model is used as input for the extractor model. The neural networks are optimized individually with the given learning rate. Here we set the representation learner learning rate as 0.000025. The learning rate for the extractor model should be filled in the next step. We use 0.0025 as the extractor learning rate. Since we utilize all the clients for training, the client fraction is set as 1. Next, the test mini-batch size is set as 256. As the next parameter number of communication rounds is set to 200, same as the classic federated learning setup. In the next steps, Atom Optimizer is selected as the optimizer, and cross-entropy loss is chosen as the loss function. Finally, the dataset folder name is given as the input, whereas the same dataset used for classic federated learning setup is used here. Then, the request is sent to the parameter server as a JSON payload with all the entered parameters. The parameter server starts processing request as a VFL game. Here at each communication round, the extractor model of each client will be optimized using their local data. The representation learner is trained at intervals when all the extractor models for the round are trained. To optimize the extractor model for each client, the representation learner model is necessary, as the extractor model relies on the output from the representation learner as its input. Hence, at each round, most up-to-date representation learner model will be shared with the local clients. At the end of the training, each extractor model will be saved in the local clients, and the representation learner model will be saved on the server. Inference is done utilizing both the representation learner and the combined output of the extractor model. The figure illustrates a comparison of metrics between the classic federated learning setup and the VFL games setup. As we can see from the figure, VFL games outperform the classic federated learning in terms of test accuracy and the training loss. This concludes our presentation. Thank you for your attention.